Okay. Okay, why isn't this open yet? Come on. Okay. You didn't notice his hair? You got it cut yesterday. No, of course not. You can't do that himself. He's jealous. What? Okay, we'll continue now. Next lesson. Yeah?
Really like rocket science.
A little bit, yeah. A little bit. Okay, ready guys? Yeah. Okay, so we're going to look at what I call for this rocket science rate of change momentum. Okay. So another way to state Newton's second law is as this, where delta P is the change in momentum and delta T is the change in time, and momentum, well maybe somebody knows this already, what is momentum? Nearly, it's mass multiplied velocity. Yeah. That is P equals mv. With units, of course, of kg meters per second. Okay, so I do actually need you to write all of this down. Got that? Good, okay, continue. Chew? Yeah. You're Bruce. Chew, you got that or you need a minute? Don't panic, it's okay. We can wait for you. You have it? Okay. So let me prove... Huh? What's up? I thought his name is Chew, no? What? I'm not going. We're not going to call him Pikachu. Do you want an English name?
I don't know. Teacher, give him one.
Should give you one.
You want? I don't know what English name.
No.
Rachel. What Ian? No.
No, not Pikachu, not Raichu.
Ian.
Ian?
Because we heard so it's like Ian.
Oh, that's a stretch. What's your first Chinese name?
We heard. It's a two word.
Two is the last name.
Yuhen. So it's like it's yeah, even.
The Ian.
Honey. Okay, we have some choices for you. Okay, not those. Ian, Stephen,
No, Steven, that's the name.
or Honey, or Jerry too. Which would you prefer?
Honey.
Huh? Brian?
Brian Chu.
Oh.
Yeah, well,
That's what he prefers. Okay. Brian. We'll go with that. Huh?
No, it's a double B and Bruce.
Double B those are.
Oh my god.
What?
Be good, Jerry. Be good. All right, we'll continue then. I think Brian is what he decided. Brian. Not Honey. No.
Oh, Brian. I know Brian.
That's not an Irish name. What are you saying?
Irish and Garubella.
Garubella.
That means like somebody is cleaning the kitchen and I think Garubella. That means no
Your pronunciation is a little bit off. I'm not sure what you're saying, but good try. Okay, so what we're going to show now is that this formula is actually the same as the one we've done recently. So this is change in momentum over change in time. So we start with U and we finish with V. So this is the momentum at the end minus the momentum at the start over the time. Yeah? So this is mv minus mu over t. So this is m v minus u over t. But what's this? Yeah. So it actually is really the same formula. Okay, write this proof down. It's a short proof. Okay, you got that? Right, continuing. So, okay, so then why bother with this new formula if F equals ma works? Like, what's the advantage of using this new formula? Well, the reason is it's very convenient to use when the time is small, or if we want to calculate something called the impulse. Does anyone know what impulse is? It is. There's another definition for it, but it is that. Now, a definition not using force though, using momentum. Yeah, we're getting close, but how? Using momentum. Does anyone know it? Impulse is the change in momentum. It's the delta P. Just the change in momentum. But that is the same thing as what you just said, Ft. You can show it's the same as that. Okay, so please note this. Okay, you got that definition? Yeah? Okay, let's continue then. Right, so here's a pretty straightforward calculation I want you to do. A 1,200 kg car crashes into the wall with a speed of 20 and is brought to rest. What is the impulse? That means, what is the change in momentum? Okay, so calculate this for me. And I didn't say this, but impulse and momentum are vectors. So they have a sign, a plus or a minus. Got it? Okay. Should only take you a few seconds. The impulse is the change in momentum, which is the momentum at the end minus the momentum at the start, which is 1200 times 0 minus 1200 times 20, which is minus 24,000. And the unit? No. No. Kilogram meters per second. Not newtons, actually. Does not actually equal newton. Because remember we said newton is kgms minus 2. Oh, yes. Okay? Continue. Okay, a hammer hits a 100 gram nail. So this is like a big nail, with a force of 50 newtons, and the nail moves with velocity of 4 meters per second. How long was the force applied? So what's happening here, you have a nail, and it's at rest obviously, and then a hammer hits it with some force, and then this causes the nail to move down into the board quickly. Some things you know the nail is 0.1 kg, and you know afterwards it's moving at 4 meters per second into the board, and you actually know the force here is 50 newtons, and we want to know the time. Now, it's not the time it takes for the nail to move into the board, it's the time that the hammer is in contact with the nail, also called the contact time. In other words, how long was the hammer touching the nail? So we're not looking for this time, we're looking for the time it's touching it. That's all, okay? So let's calculate this now. We can know the impulse. The impulse is this, which is this, which we can know. Afterwards, its mass is still 0.1, no matter what. So this is 0.1 minus 4 minus 0. And why am I saying minus 4? It's going down. So this is minus 0.4 kilogram meters per second. Well, that's fine. But how does that get me the time? Well, yeah, I know that F equals impulse over time. So that means impulse equals, as you were saying, Ft. So we can say this is equal to Ft, which is minus 50 T. So we have our answer. The T is 0.4 over 50. That's 0.8 seconds. No, it's not. It's 0.08. 0.08? Okay, so that's 80 milliseconds. Okay, so that's what I was saying earlier, that this formula is useful for working out small contact times. Okay, so write this one down and then we'll have a look at another example. Zoom out? Oh, you need to see the top? Got that yet?
So why that delta T is 88%?
Huh?
That's 80%.
Milliseconds. Milliseconds. Oh my goodness. OMG. 10 minus 3. Milli. The first lesson.
Oh, minor.
No. Milli.
What's the meaning of that?
Milli. Mega, giga, milli, kilo. Continue?
Yeah.
Okay. Right. Okay. Here's another similar one, which I think I'll let you try now. A 250-gram football is at rest, and the player kicks the ball, and the ball moves with a speed of 10 meters per second. What is the impulse? And then the player's foot is in contact with the ball for 100 milliseconds. What was the force? Okay, I'll let you try this one now. Then we'll continue.
The second that was word is we have community of the extreme.
Which word?
What word? We have to calculate
Yeah, what was, calculate the force. Got it? So what's the impulse here?
2.5.
2.5. Very good. Kilogram meters per second. Good. And then the force? 25. Okay. We'll continue then. Right, so another big advantage of using this formula is it lets you calculate the force provided by rockets or other propulsion systems. So think about the hot gas coming out of the rocket. It has a mass m and a velocity v, but the gas was at rest, therefore its momentum changed. This, together with Newton's third and second law, will give us a formula which I'm going to go through now. So let's explain the idea here. So what happens is you have your rocket, and you have your gas inside of it, and the gas comes out bit by bit. You know, maybe we could say delta M per delta T. So you have all your gas inside, and maybe every second some of it comes out as fire. Yeah? Not love. Fire. Okay. So let's look at one piece, for example. Let's say this piece of gas which is about to come out. So this has a mass of delta M. What's its velocity? 0 at the moment. But then when it's fired out, its velocity then is not 0. So its momentum has changed. It has an impulse. So the impulse is the change in momentum. The M doesn't change, but the V does. So it's mv minus 0. Sorry, I was using delta M. The reason I'm using delta M is to mean a small mass. So let me just rewrite that a little neater. So yeah, delta M V minus delta M U. So that's delta M V minus U. And that's delta M. The U is 0 and the V is quite small as well. Or I mean, it doesn't have to be small, but we usually use delta to mean a small amount. So that's V. Or sometimes people might write it here as delta V. Doesn't really matter. And also, I should really put in minus, because I know this V here is a negative. So I just want to emphasize it's going down. So we have delta P equals mass multiplied velocity. Or just mass multiplied velocity if you prefer. It doesn't really matter. But if I divide both sides by time, this will become the force. But this one is going down. But just like with the balloon example we saw, Newton's third law says that there will be a reaction. When this gas pushes out from the tank, the rocket will have a reaction upwards. And that will be equal but opposite to this force. So the force acting up will equal this. Now quite often the time is 1 second. So we look at the gas coming out per second, which makes this formula simplify because that's just a 1 second. So we have F equals mv, or if you want to write it as delta M, delta V. In other words, to simply explain it, if you have a rocket and let's say the gas comes out at 2 kilograms per second, and the speed it comes out at, we'll say, is 10 meters per second, as an example, then I know the force up here will be 20 newtons. It's simply a matter of multiplying the mass per second by the speed. And this will give us the up force, which is called thrust force of the rocket. It's just the mass that the gas is coming out at multiplied by the velocity of the gas. Okay? This is quite a simple formula but quite useful because now we know how much force the rocket has. If you want to make the rocket go faster, you have two choices. You can have more mass per second, or you can have the gas come out faster. But what's nice here is it doesn't only work with gas. This could be a liquid. Yeah? Have you seen this before? I'm sure. Have you not seen the experiment with the bottle? Yeah. And then you release the cap and like the soda, the liquid shoots out the bottom and the bottle fires up then. The same idea as that. Okay, so can you write this down? Especially this is the key result here.
I'm just going to
Yeah, I don't worry too much because I don't really think it's not in the proof that's on the exam. At least have the result down. Need me to zoom out, Bruce? Uh-oh. That means battery time. Okay. What's the password? Come on. It's not dead. It's still alive. Don't worry. Please, that's Windows. You would definitely know this is not Windows.
What is this called?
Linux. You know Linux?
I thought it's like you going to like.
Yeah. It's a distribution of it. Okay, do we have this? Okay, got that? Continue? No, I still see writing. Got that? Okay, now we continue. Right, so here's a simple little example. You have a rocket of mass 4,570 kg. At launch, the hot gas is propelled at a velocity of 4,462 meters per second, and each second, 7,485 kg. Wait, that's ridiculous. Oh, something's wrong here. Boom. Let's make the rocket bigger. We'll add a couple of more zeros. Wait, actually, the mass of the rocket's not important because I'm only asking for the upward force. Yeah. So ignore. Let me just cover this up. Not important. Right. Calculate the upward force. All good? What's the force? Pretty big, I'd imagine. So what's it in kilonewtons if you divide by 1,000? So you would need to go in meganewtons, wouldn't it? So 33 meganewtons. Okay, did you get that? 33.4 meganewtons.
Yeah.
Yeah. Okay. Right, now this last one is difficult and important, so let me work on this one. Okay, so it was a windy day and a physics student was walking home. The student stops for a moment to calculate the force he is feeling from the wind. The wind was blowing at a speed of 12 meters per second into the student. The student is 1.6 meters tall and 40 centimeters wide. It's Jerry, is it? Are you 1.6?
I will manage to do it.
Actually, yeah. I think this could be Jerry. Yeah. The density of air is 1 kilogram per meter cubed. What was the force felt? Okay, so let me just draw what's happening here. And I'll represent the student by a rectangle. So this is the student here. This is the student, believe it or not. This student is 1.6 meters tall and 0.4 meters wide. And what's happening is you have the wind blowing here, and the wind has a speed of, 12 meters per second. And yeah, you know the density of air is a kilogram. Now what I like about this question is that all the information you can easily find out. You can know your height, right? You can know your width. You can know the speed of the wind by just checking the weather. And so, with that information, you can actually work out how much force you feel from the wind pushing on you. That's not the wind, don't worry. Okay, so watch carefully now. This is a tricky one, and I should say I've seen this in the exam once or twice. It's a hard example of this type of lesson, for this lesson. So the wind is blowing at 12 meters per second. And remember, for these problems, we look at the time over 1 second. Okay? So if we're only looking at 1 second, then I only care about the wind that's 12 meters in front of him. Why wouldn't I care about the wind which is more than 12 meters in front of him? It doesn't reach him in 1 second, so we don't really need to care about it. Okay, so let's look at what's happening here. You have all this air which is moving, and then it hits him, and what happens to the air? It comes to rest. This is just like the rocket, except opposite. The gas is at rest, and then the gas moves. Here the air is moving, and then it's at rest. So you still have your impulse. It's the change in the momentum. Which is zero here, the V or the U?
The V.
No. Sorry. Yes. The V is zero, so we have minus mu. And we know the U, so that's minus 12m. If we divide by the T, which is 1, we've now just worked out the force. So the only thing left for us to do is to work out the m. We don't know the mass of the air, but we do know the density of the air. So if I use my mass, my density equals mass over volume, then I can work out the mass. Now this force is a minus, so the reaction he will feel will be a plus. So the force, the reaction force, will be plus 12m, which will be 12 density by volume, because I can make that the mass. Do we know the density? Yeah, what did I say it was? 1. So it's just equal to 12b. Do I know the volume? I can get it, because it'll be 12 and then I have to do here 12 times 0.4 times 1.6 and put that in. What is that, please? 7.68 meters cubed? Okay, so what 12 multiplies 7.68, please? So it is it's just like there was 92 newtons of force pushing the student. So if the student wanted to move, how much force must they lean forward? More than 92 newtons. Okay, so it's literally just like he feels a force of 92 newtons pushing him, and he will have to, if he wants to move, or at least stand still, push forward with 92 newtons as well. Yeah. This is a harder one. Not impossible, but definitely harder. So please write this one down. Oh yeah, this is what is normal. Typically you always look at these problems as happening over 1 second to figure out what the force is. Because all the units are in per seconds. So like, if you want to know the change, if I say what is the impulse, what is the change in momentum, I always mean for these problems over 1 second of time. How does the momentum change? So this is just the standard value here for these problems. Got it? Still writing? No? Okay, can I continue? Yeah. Any questions with this? Is it okay? It's a hard one, but it's not impossible. It's just a harder idea. Yeah. Okay, let's have a look here. I don't know if I have another example or if we're going to practice some questions. Yeah, no, we're going to practice some questions then. Okay. Enjoy number 5. It's a difficult one.